Good afternoon. My name is David Gustavsson. I'm an engineering VP for XIO, and we're going to talk a little bit about some of the technologies that we do and how it makes a difference. Managed reliability. We have a term that we refer to in the industry as managed reliability. The point is, if you take reliability as a design objective and try to manage it, it's very different than just do a static objective up front and then say, hey, it is what it is. You're not going to change it. This goes back to the conversation we had earlier regarding what happens to drives in a lot of system vendors' back end. Something goes wrong, they found that there's a glitch of some kind, and there's a deliberate choice to say, you know what, the disruption of this one drive not behaving is going to be adequate, that it's cheaper for us to deem the drive bad and push it out. So that drives then a tremendous amount of drives being returned to Seagate with no trouble found. Anywhere between 50 and 85%. And there's different numbers depending on drive model, system vendor, and frankly, even drive firmware on some of the, or not drive firmware, but system firmware on some of the vendors, right? So some firmware revisions are more sensitive, if you will, in throwing out the drive. So we started the whole project being a part of Seagate. So we had unprecedented access to information regarding what's causing the drives to fail and the real failures and what can we do about it, right? So a tremendous amount of drives don't have a problem at all. So if you can eliminate that, that's a huge chunk to start with. But the ones that do have a problem also exhibited certain behavior regarding what the problems was about, mechanical versus electronics and magnetics. And it turns out even if you have mechanical and magnetic problems, does not mean that the entire drive is broken. So now we're getting into the point regarding what happens when a drive fails. So we focus on two things that we've talked about. Passive hardware design, meaning treat the drive right in the environment and enclosure, and it will treat you right, both in performance and life cycle and reliability. It makes a difference how you treat them. And also, take the time to figure out what's actually going on with the drive. Don't just consider that because it was, in your mind, misbehaving, throw it out. So we have spent a tremendous amount of time integrating at a drive interface layer to understand what's going on inside of the drive to a much bigger degree than what the traditional vendors do. We call it, when in doubt, check it out. Not when in doubt, throw it out. There's a philosophy difference there regarding, do you care about what's actually going on with the drive, or do you consider that a disposable components that you need to be able to throw out? And by driving an integration knowledge and understanding what's actually going on inside of the drive, we can also change how we treat the drive from a component perspective. It's not, we don't have to treat it as one component anymore. A drive has a lot of different components, it turns out. A lot of platters, a lot of heads, right? And if we can map our data distribution algorithm, and that's why we created a different distribution layer underneath RAID to be able to create, if you will, a RAID virtualization layer that allows us now to also deal with a head going bad, not an entire drive going bad. So in effect, what we've done is that we've changed a drive failure from being the entire drive going bad to, we can take the drive and look at it and say, 3 out of the 4 platters are still fine. Let's keep using them. So now we have changed the failure blast zone and dynamics from an entire drive to a certain capacity amount. So RAID algorithms that we have and distribution architecture is built with ability to deal with a shrinking drive in mind. So we're pretty unique in this case. While you buy a 900 gig Seagate drive, if for some reason that drive can no longer provide 900 gigabyte to you, it considers itself broken. It will tell you, I don't work anymore, right? And the entire 900 gig is gone. In our case, we have firmware inside of the drives that we have developed at Seagate that runs our stuff, that has a remanufacturing capabilities, that takes the drive, it goes in and does a platter by platter, head by head diagnostic, and identify if we can map one of them out, reformat the drive, and use it as a less capacity. So instead of being a 900 gig drive going to 0 gig drive, it's a 900 gig drive that might go up to an 820 gig drive, right? Or so. And what happens now is that drive failure that used to be, I got to replace the drive, pull it out, plug a new one in, and keep running, become, Nothing, because we have built-in spare space that is distributed across all the drives, 20% of it. So we invest 20% upfront spare capacity across all drives, okay, that we then use, if you will, such that we can continue to provide the user capacity that the system was sold as, such that if you buy a 20 terabyte system, you will always have a 20 terabyte system. It's just that we added more capacity built into the system up front, such that you don't see it in the beginning, if you will. And what happens there is, in effect, all drives contribute performance for all volumes, and since the distributed sparing is across each drive, right, you don't have this sparing performance penalty of having a dedicated spare. Make sense? So what happens here is the data distribution allows for granular remapping of the surfaces such that we can deal with sub-disk granular failure to extend service life. Make sense? This is far past bad block replacement. Bad block replacement still happens inside of the drive, and the drive is trying to do its job at a sector level to try to remap potentially bad sectors or weak areas, right? What we do is, once there's now a significant event and the drive says, I can no longer carry this set of information, we can map around it.
So your ability to do that, I imagine, would mean you either have access to firmware that other vendors may not have access to.
That's correct. We have specific XIO firmware in those drives that are developed specifically for us from Seagate, and we qualify and develop that drive firmware with Seagate inside of our system. So at the same time, we also lay out 520 byte sectors instead of 512. It's all diff protected, every single sector, with line speed, data integrity checking to ensure that we don't return the bad block or a broken set of information.
And that CRC checking is done in the drive?
CRC checking done inside of the controllers. So we do diff, so we do sector size 520 as a ubiquitous, if you will, container, and then we generate the CRC, of course, going out. We can then read the CRC coming back, and should something has changed in between, then it doesn't match, and we can figure it out. So data rot, if you will, or silent data corruptors is no longer there. And then on top of it, we overlay with locational information, so the VBA, if you will, of that LUN information is also there, such that should there be a mapping issue for some reason, we can identify those.
And by controller, do you mean the drive controller, or do you mean the bus controller?
The system controller, the x86 architecture scenarios, yes.
Okay.
One of these, I think.
So we use, yes.
That CRC is hardware checked, or is that?
Yes, yes.
In the controller, okay.
We use the front-end fiber channel controller to do that before it leaves the bus, such that we can identify that every potential byte has been checked.
Does that cause any performance problems due to like fragmentation or anything?
Nope. That's a huge pride point of us, to be able to do that at line speed and knowing that every bit we gave you was the one that you gave me, right? And we know that. And it's one of those things that I built, been a part of building a couple of different storage systems, and in the beginning, we spent a tremendous amount of time before we took the product to market, making sure this was it, because when you get what we call a diff error, data integrity field error, it means something's not right in the software. And the beauty of having that built in means you know it's solid, because you don't have data corruptors, you don't have mapping problems, you don't have pieces. So in the beginning, it was a tremendously useful debugging tool from a system perspective to make sure virtualization, RAID, and everything is done correctly. It took us, frankly, almost 6 months longer to get it to market because of it, but we know then, right? It's good. Big difference.
4 of those months were because the T10 diff code from the drive vendors didn't work, but.
Well, so it turns out we don't use that, right? But what we say is format to 520, and then we dump the information in there. So
I'd like to bring up a point. So hopefully that answered your question earlier about, how do you replace a disk when it fails? Well, what we're doing is we're looking at a disk as not a disk. We're looking at it as 6 surfaces, for example. So if a surface fails, then we can take care of that, right? By looking at it from that level and not as a disk level, we also look at how we rebuild data and how impactful that rebuild can be, right? Because that really affects the performance of the system as it's under load. So maybe, yeah, you can cover your points on the rebuild.
I asked that question because somebody on Twitter posted, what happens, I guess there's a customer that deployed
one of your units, and they had a RAID 0 and the drive failed.
RAID 0, yeah. So in the beginning when we had...
What happens then?
Right, no, clearly. So in the beginning we were actually offering RAID 0. And what we learned pretty quickly was that was loading the gun, putting it against the head of the customer and asked them to not pull the trigger, right? And we frankly decided after that, you know what, that was not kosher because there was a misunderstanding and maybe even a misrepresentation of us giving the indication that our RAID 0 can handle disk failures. If you have a RAID 0 data set, you don't have the redundancy in the data set to actually build up the data that was lost, and that's just mathematics, right? So we have since then actually turned off the RAID 0 option in our system. So we do only RAID 1 and RAID 5. So drive failures contains a redundant data set so we can rebuild those pieces while that drive is offline. Hopefully that answered the question.
So what happens when you have more than 20% disk failure or component failure?
So if you get to the point where you have actually exhausted what would be equivalent to 20% capacity of degradation, not 20% of drives normally, because it distributes across many drives now. What happens is that we have a replacement process where we can replace a data pack, and this goes back to how we pair two systems up to provide same volume served by both systems. You can now non-disruptively pull one data pack out, plug the other one in, and continue with your services.
It's not customer replaceable then?
It's not customer replaceable, that's correct. It's a service that we provide, and it's a part of our 5-year hardware warranty that we bring to the customer at day one. So when they buy our system, we stand behind it for 5 years, and should that happen, we'll send service out to make that happen.
And how often does that happen?
Yeah.
Have you done that?
Not very often. I mean, there are always a distribution curve on all failures, right? So even though the design for the norm is it doesn't happen, right? There are some incidents where you have enough of stochastic anomaly, or whatever you want to call it, right? Where you see that happening. But, so we have had a couple of customers that we've had to replace this on, and I'll be fair on that. But compared to the hundreds or thousands of drive replacements that it would equate to, it's nothing, right? You're talking about, we got, what, 6,000, we probably have 150 to 200,000 drives in the field or so, right? And we have a few of those replacements, it's nothing. So this is about service avoidance and service extension, not complete elimination. There's no such thing, right? So hopefully that explains what we do with a drive failure. And that is very, very important, because if we can now optimize for drives being integrated, we can design the architecture differently. We don't have to have the replaceable drive architecture. And that's the point behind the data pack design and what you see. So we don't let the drive be accessible to the user. We even have a solenoid on the data pack to avoid it being erroneously pulled out if it's the wrong one or so, right? The whole point is create a unit that is very, very well contained, very predictable, very well understood and profiled. And this one module now is not just a module, it's a building block for much, much bigger scale architecture. So while we present this as a 3U unit, and most people think of it as, oh, it's a small box kind of thing, this really takes it to large scale operations, and it's a matter of how you take these and stitch them together as the backbone to build a bigger scale architecture.